The Sigma Score Calculator spreadsheet you have available in the class is simply intended to help you work out some of the math of calculating the defects per unit, defects per million opportunity, and Sigma score associated with your processes. So you should be using some variation of this spreadsheet in any project that you work on where you want to quantify the quality factors related to measuring your processes over time. So this first version is a very simplified version. We would just look at the distinction between a customer Sigma score and an internal process Sigma score. They can be different for a wide variety of reasons. So suppose we're trying to come up with a quality model to measure from a customer's perspective whether some garment that the customer wants to buy is defect free or not. So we'd have to make a list then of all of the garments, the different things that could be wrong with a garment over time. It could be the wrong size. Okay. So wrong size. Let's keep it simple and assume that's the only thing that can be wrong with it and say there are no other defects going on. So we delete the rest of these. We're deleting them because the opportunities that are being counted here are actually a count function in Excel of those things. So we don't have to delete the extra rows, just now we know that there's only one opportunity for a defect in the garment. It might be the wrong size. So to keep it simple, we'll look at the internal process the same way, measuring a garment. But on the internal side, we might look at something different. We might make it too long. We might make it too long or short, so wrong length. Okay. Too wide or narrow. Okay. Too tight or constrained. So inside the process, we may have a different list of defects that would cause all those things to happen. So each of these things is something that could be wrong at the same time in the garment. On the customer side, all that determines that it doesn't fit them. It's the wrong size. But inside the process, it could be very, very different than that. So the trick is to estimate how many garments are we talking about. Maybe we're talking about 1,000 garments a month that are being produced and sold to customers. And keep it simple, we'll make it the same on both sides. Okay. So on the customer side, when there's 1,000 garments, there's 1,000 opportunities to mess up, since there's only one thing that can go wrong on each one of them. On the process side, there's 3,000 opportunities to mess up because there's 3 opportunities per defect going through. So let's assume, just looking at this, that from the customer standpoint, 10% are perceived as being the wrong size going through. Okay, or 100 becomes the number that's relevant there. So 100 tend to have the wrong size. On our side over here, maybe again 10% going through, which would give us 300 that are too long. Let's make that 10% on each one as we go through. So 300. So suppose we're really bad, and 10% of the time we have too short and too long, we have too wide or too narrow, or too tight or too constrained. Not necessarily the same ones as the customer perceives, but in essence we're counting as we go through. So you count the number of defects in the process going through, the actuals. So whether you're recording the actuals or some estimate of them, the spreadsheet can be done in either way. So to take a discussion, I'm using estimates of roughly 10%. It could be even that I have 15% are too wide or narrow going through, but that doesn't necessarily show up in a change in the way the customer perceives it, because I could be in or out of spec on these dimensions, but still have the customer perceive me as fitting. So again, I'm going to work that out. The challenge is to look through your requirements and figure out what are the opportunities for the customer to see a defective and what are the opportunities for a defect in your process that will lead to those. And then the math becomes pretty much the same. So we have a total number of defects is the total of that column on both sides. The total opportunities is repeated from above 1,000 opportunities on the customer side, 3,000 opportunities on the producer side. And then we calculate the defects per unit. The defects per unit are going to be the number of defects divided by the number of units. So in this case, on the customer side, a defect per unit of 0.1. On the supplier side, the defects per unit, I pressed help by mistake, sorry. The defects per unit are over 1.05, because we have 1,050. If I can stop pressing F1, that would really help, wouldn't it? Okay. We have our 1,050 50 divided by the 1,000 garments is we have more than one defect per unit. We actually have more defects being calculated than we have units. That's okay. So it's not good, but the calculations are correct. And then we'll do the adjustment of that per million. So the defects, total defect count times a million divided by the number of opportunities is the defects per million opportunities. And here again, the defects per million opportunities. So that's the straight math. And then the sigma score gets calculated for you in the spreadsheet. As if it's 0, it assumes 6 sigma, but otherwise it takes the norm's inverse plus the 1.5 6 sigma shift that we've talked about in our class. So looking at this very, very simplified example, we have a customer sigma score of 2.78, which isn't particularly good. If 10% of our product is no good, that's not real great. On the process side, though, we have an even lower sigma score of 1.89. It's typical that the process sigma score won't be as good as the customer sigma score. It's not an absolute requirement. If you're good at making defects in your process that the customer never sees, you could have a very, very different process defect rate going through. But in general, you're going to find your process sigma score is lower than your customer sigma score. Now, you don't try to fix your sigma score directly. You don't come up with an improvement project to say, let's attack these wrong size. Or if you do, you ultimately have to trace that back and say, what's causing the wrong size? You say, well, it's these 3 errors are causing it. And the one that's the worst is the too wide and too narrow. So perhaps we should go after a Six Sigma project to fix our width issue in our manufacturing process, and that's the way it will work. And that's the way most process improvement works. We improve our customer Sigma score by attacking the low spots or the weak links in our process Sigma score. So process Sigma score will drive, if I can increase this process Sigma score, what I'm going to find is I'll have fewer of these defects, and likewise I'll have fewer of the wrong size defects. So I will improve my customer Sigma score typically by improving my process Sigma score, which is why Six Sigma quality management is largely about improving your processes and reducing your variation over time. So that's a very simplified example of some of the math of DPU and DPMO. But it won't tend to do for what you have to be able to do on most of the projects that you'll do, because quality is more complicated than that. So I'm going to bring in a second version of that chart where I've gone hierarchical. The math is going to be the same, so don't be intimidated by this. But assume you have some kind of a hierarchic structure that you have to work with. For instance, in a cashiering application, we might have more than one level of detail we have to work with. So if I just look at in a cashiering situation at the number of checkouts that I do, and within those checkouts, how many items do I check out? And maybe I don't have any other dimensions that I want to work with there. Suppose I process 500 checkouts in a day in a cashiering situation, and on average I have 10 items on each cashiering situation. So I actually have 5,000 units going on here. That's what you're looking for, is how do you define the leaf level units? In this hierarchy, it's the 10 times the 500. I didn't need the lower 2 levels. On the production side, it could be different. I'm going to deal with the checkouts again probably, and I want to be able to do the items. But from a process standpoint, I'm interested in the individual actions or transactions that I carry out. So maybe there are 7 transactions for each of the 500 checkouts on average and the 10. This requires me to go somewhat generic to understand that the defects for the actions and transactions would be the same. But in essence, this is a model that says the customer has, on the customer side, I do 5,000 things a day. I check out an item. On the process side, I say I do 35,000 things a day. I do one of the 7 actions or transactions associated with checking out an item. And I want to manage the process at a lower level of quality detail than I do the process going on. So what I've done here is I've labeled the first 4 levels here A, B, and C, A, B, C, and D. They're just shorthand ways of referring to the levels. And I'm using A and B. I'm not going to use C and D in this case. Over here, I'm using W, X, Y, Z to do the same thing. It's a generic process, so that the labeling down below will correspond to that. So again, I have a 2-level hierarchy on the customer side, a 3-level hierarchy on the process side as I go through. So then I go through just like I did before, and I start looking at what are the defects that can occur. Well, this one is just the A defects, the actual A. What can I do wrong at the checkout level that doesn't involve the individual items? So something I do once per checkout. So if a customer says the cashier was unfriendly, that might be a defect that occurs at the cashier level independent of the product. So I want to call that a defect at the A level, which is just checkouts. Then I might come down to the AB level. And what can happen on the items themselves? I could end up scanning the product, so I check out the wrong product. Oops, can't spell. Okay. I could have an incorrect price. I could have a poor bagging. Okay. Or I could potentially produce the wrong change. Now these are things the customer would care about, not anything that can go wrong in the process, but something that would cause the customer to believe the item was not being processed clearly. So then I'm going to eliminate the lower level. Okay. So on the customer side, I've only got those two levels. So as I scroll down, I have places I could have entered the defects had I gone to an ABC level of hierarchy, which I didn't use. So I'm going to eliminate these defect names. And the ABCD hierarchy, lowest level, which I did not use, I'm going to eliminate that. By doing that, you're zeroing out the number of opportunities. You don't have to clean up the spreadsheet any more than that. So what I have now on the customer side is 5,000 units being processed, where there's one opportunity at just the 500 level and 4 opportunities at the item level. So this is the lower levels tend to dominate. It's 20,000 opportunities a day to do something wrong at item level, but only 500 items a day at the higher level. So there's 20,500 opportunities to do something wrong every day. So that's where the hierarchy helps, because not all defects and problems occur at the same level. I would then repeat the process over here on the process side, and it's going to be related. So do I have a correct greeting, or an incorrect greeting rather? That might be what I want to measure here. At the second tier of the item, perhaps the cashier is supposed to look for opportunities to upsell, warranties and things of that nature. So maybe I should be doing that. That could go wrong at the second tier. That's the WX, just checked out items, these 5,000 times a day. And then the third tier is the action or transaction. So again, down here, I could be dealing with the wrong product on the fulfillment. I could do an incorrect amount on my entry. I could take an incorrect action. I could be too slow or delayed. Okay, so there's 4 defects there, and I can just blank out the rest. Okay, so I have that 3-tier model going on here. I did W, X, Y are used, and I've entered data for those levels. Again, on this side, I still did not use the WXYZ level, so I don't have that lowest level going in. So I'm testing it. I've got zeros on all the numbers, so I've got a 6 sigma score because I haven't entered anything yet. But again, I go off now in the measure phase and say, how often does that happen? Well, I survey my customers, and they find that 10% of the time they consider the cashier unfriendly. When I talk to them about their experience with this, maybe 1% of the time they get the wrong product, 2% of the time they get the poor bag, incorrect price. They're often unhappy with the bagging. 8% of the time it's done wrong, and they say, well, 1% of the time they get the wrong change. So I can fill in those numbers and get that kind of score. So based on that estimate of the defect rates associated with it, my customer sigma score becomes 3.39 as I see my way through. On the other side, I might find that management observes the workers and finds actually that 40% of the time they don't give the correct reading. It's fortunately only 10% of the customers consider it unfriendly, but in fact 40% of the time they don't meet our standard for the greeting. Turns out that 70% of the time they forget to do any kind of upsell, and down here on the wrong product they actually only do the 1% of the time the customers perceive. An incorrect amount actually happens 15% of the time. An incorrect action might happen 20% of the time, and the process takes longer than expected 30% of the time. So we're very error prone in our processes. Hopefully we have forgiving customers on the other side who don't consider that a defective. So having filled in that model, I can see that the internal process sigma score would fall to a 2.4. So again, you can download the spreadsheet and take a look at the math here. But the key measures are you can measure the defects per unit, but that's difficult to compare. It's hard to compare the DPU of the 20,000 units that I'm dealing with on this side. I'm sorry, not 20,000 units. The 5,000 units I'm dealing with here is very different than the 35,000 units I'm doing here. So when the units are dramatically different, the DPU isn't particularly useful across products. The defects per million opportunities does, in fact, harmonize the data across. You can compare that. So the defect rate for the process is much, much higher, 184,000. You can actually look it up. I gave you a DPMO chart. You can look up the 184,000 in the chart and see that it's right in here at about 2.4. And sure enough, that's what we calculated we went through. The 30,000 in the chart is farther down here. That would be about between 3.4 and 3.35. And we got it at 3.39, so that's roughly where we'd expect. But you can look up the basics if you know the numbers here in the chart. So that is how you do the calculation and work on your hierarchy. So the biggest challenge is actually to take it as two steps. What are the hierarchic views of your product? Because most things involve a hierarchy, but make sure it's a hierarchy. It has to make sense to multiply these things to get the units. If you're talking about differences in your product that you would have to add them up, that's different than having a hierarchy as you go through. So make sure it's something where you would want to multiply the number of products. So the number of items in the item bank, the number of responses per question, the number of questions on an exam, the number of candidates in a month. Make sure the things you're categorizing in your metric model would be things that would get multiplied to come up with those units. Here's another example we can take a quick look at. Here's one where it's 3 dimensions on each side, so it's very, very quick. Suppose I'm doing order processing, and I'm processing line items and shipments per order as I go through on the customer side. So I do 1,000 orders a month with 5 line items that on average require 1.1 shipments. So I have 5,500 order line shipments a month on the customer side. On the process side, I've got orders and line items again, same 5,000. But here I'm looking at the transactions that get done for every shipment. Shipment's just one transaction that the customer sees, but maybe there are 12 transactions for every line item order that has to be processed. And that's what I want to count on the process side. Because these are 3-dimensional, I can basically skip the 1-dimensional and 2-dimensional defects on this page, come down to the 3-dimensional and say on the customer side, the shipment item could be incorrectly filled, arrive late, arrive damaged, or go to the wrong location. On the process side, that could be because I have incorrect quantities, incorrect assignments, delayed processing, incorrect qualities, or incorrect processing. And again, I make a guess at what some of these. In your measure phase, you're not guessing anymore. You go out and try to actually figure out what kind of defect rates would I expect to have on this basic process. And again, because it's a 3-dimensional model, I'm able to leave the 4th dimension empty and go ahead and do the math down below. So on the customer side, out of 22,000 opportunities to mess up, I messed up 1,100 times for a 0.2 DPU, a 50,000 DPMO for a sigma score of 3.14. On the process side, I had 3,000 opportunities, 39,000 defects for a DPU of 0.65, a DPMO of 130,000, and a sigma score of 2.63. Again, the benefit of having the model is that you've quantified things in a way that's consistent across many Six Sigma projects, and now you can use your quantities to drive your improvement. Ideally, you're trying to improve the customer sigma score, so you're trying to make one or more of these defect types go away to improve that score, but you can't attack them directly. You go to the process side, say which of these defects on the process side are causing them. So maybe I want to attack the arrived damaged problem because that's my biggest opportunity on the customer side. So I want to come over here and say which of these defects would result in arriving damaged, and maybe incorrect processing on the shipment side. So it's not necessarily the biggest defect because incorrect qualities might not result in damaged arriving. You got to look at which of the things within the transactions might result in that particular defect and attack that. So again, you always attack a Six Sigma project by trying to improve the process sigma score, knowing that if you've picked the right project, it will have as good a change as you can get on the customer sigma score. So yes, we always want to improve the customer sigma score, but we do it by focusing on the process sigma score as we go through. And then lastly, if I were going to bring this into an engineering report, it's a lot of gunk, tracking this up. So typically what I do after I finish the math is I go through and clean up the spreadsheet so it looks something like this. This was a particularly easy one because I only had a 3-dimensional model with no extra defects. But go ahead and hide the rows of the spreadsheet that you're not using. Be careful about deleting them because you might find later that you discover defects at those levels that would have gone at the rows you deleted. So it's better if you hide them. Another reason to hide them is often when people start deleting rows from complex spreadsheets, they actually break some of the equations that are doing some of the math. So hide the stuff you don't need in case you want to bring it back. But this is the exact same example. I've simply hidden the information from the multiple dimensions that didn't have any defects going on in the process. And I can use this now as a figure in my engineering report to let the reader of my engineering report know what my starting position is coming out of the measurement phase.